Now I am become death, the destroyer of worlds.
On July 16, 1945, Julius Robert Oppenheimer unlocked an unprecedented power, one that held the potential to sculpt or shatter the very future of mankind. The path that led him up to here was paved with significant events that effortlessly aligned as though he was destined to become the father of atomic bomb. This is the story of a visionary mind and his journey that ultimately led him to become the architect of a world-altering event, the atomic bomb. Julius Robert Oppenheimer was born into a Jewish family. As a child, he was captivated by science and had a wide range of interests, including collecting minerals and exploring poetry. His parents supported his interests and provided him with ample opportunities to nurture his talents. He enrolled in the Ethical Cultural Society private school, where he developed a deep fascination with languages. He would play unusual games. He would ask people to pose a question in one language and then respond to it in a different language. As a student, he excelled in his studies and conducted advanced experiments even before reaching double digits. It was during his high school years that his passion for chemistry was truly ignited. He graduated shortly thereafter in the year 1921. In the spring of 1922, he journeyed to New Mexico for the summer. He loved New Mexico and once mentioned, "My two great loves are physics and New Mexico. It's a pity that they could not be combined." Little did he know that in about 20 years, he would be the catalyst behind their union, ushering in a new era of the atomic age. Oppenheimer began his undergraduate studies at Harvard. Initially enrolled in chemistry, he soon realized that his passion was truly in physics. He sought out Percy Bridgman, a renowned physicist and future Nobel laureate, to mentor him. Oppenheimer admired him as a teacher. Despite occasional episodes of depression, Oppenheimer remained dedicated to academic excellence. In 1925, he graduated summa cum laude in chemistry. After completing his undergraduate studies, Oppenheimer stood at the edge of a new academic chapter, eager to further explore physics. He asked his professor Bridgman to write him a letter of recommendation to Ernest Rutherford. Although Rutherford did not accept him, he referred him to J.J. Thomson. Oppenheimer began his graduate school at Cambridge. There he met influential figures like Ernest Rutherford, James Chadwick, Patrick Blackett, and C.T.R. Wilson, with Blackett becoming his mentor. However, Oppenheimer found Cambridge to be more of a prison than a physics mecca. In November 1925, he wrote a letter to Ferguson, a friend from the Ethical Cultural Private School, expressing his difficulties. He found the lab work tedious and felt like he wasn't learning anything from it. He also noted that the lectures did not meet his expectations. By the end of the autumn term, Ferguson recognized Oppenheimer's severe depression. Under Blackett, he studied thin beryllium films for electrons. He was not fond of experimental physics. Things took a turn for the worse when Oppenheimer made a regrettable attempt to poison Blackett, almost resulting in his expulsion. Although a rough period, Oppenheimer's time in Cambridge was useful for his development as a physicist. He had close encounters with many of the world's leading theoretical physicists, including Bohr, Dirac, Chadwick, and Born. Niels Bohr had a lasting impression of Oppenheimer and expressed that he was a gifted individual with exceptional intellectual abilities. Bohr was Oppenheimer's god, and he was his prophet. Inspired by Bohr, Oppenheimer shifted his focus from working on beryllium films to theoretical physics. Robert traveled to Gottingen, which was considered the hub of theoretical physics. In Gottingen, Oppenheimer had the opportunity to interact with extraordinary scientists such as James Franck, Otto Hahn, Paul Dirac, and John von Neumann. At the time, these young men had no idea that they would meet again, but that encounter would change the world forever. Shortly thereafter, Oppenheimer used quantum theory to explain molecular properties, which led to a joint paper with Max Born titled On the Quantum Theory of Molecules. This very important piece of work introduced the influential Born-Oppenheimer approximation, a significant breakthrough in applying quantum mechanics to comprehend molecular behavior. Oppenheimer's work also laid the groundwork for future advancement in high-energy physics. On May 11, 1927, he successfully defended his thesis on photoelectric effect in hydrogen and X-rays. In 1929, Oppenheimer came back to the US with the goal of introducing quantum mechanics to students in America. In his early years at Berkeley, students struggled to follow his lectures. However, over time, he developed into a skilled, and charismatic lecturer. Ernest Lawrence, a prominent experimental physicist, was already a leading figure in his field when Oppenheimer arrived at Berkeley. Lawrence had envisioned building a machine capable of penetrating the atom's nucleus. By early 1931, he had constructed his first crude particle accelerator and named it cyclotron. Cyclotron eventually earned him the Nobel Prize in Physics in 1939. Oppenheimer's encounter with Lawrence at UC Berkeley is a particularly important event, and he would play an important part in Oppenheimer's future involvement in the Manhattan Project. Oppenheimer did excellent work at UC Berkeley. In his paper on the theory of electrons and protons, he proposed the existence of the positron, that is the antimatter counterpart to the electron. His groundbreaking work on neutron stars, conducted in the late 1930s, preceded the actual observation by astronomers in 1967. In 1939, Oppenheimer and collaborator Hartland Snyder published a paper titled On Continued Gravitational Contraction, proposing that stars with a core mass beyond a certain threshold would indefinitely contract, forming black holes. Oppenheimer's fascination with the mystical led him to study Sanskrit. With his linguistic talents, he quickly immersed himself in the Bhagavad Gita, finding it both easy and beautiful. He considered it the most profound philosophical composition in any language.
At Berkeley, he'd read the Bhagavad Gita and learned Sanskrit, and was really taken by the charm and the kind of general wisdom of the Bhagavad Gita.
One of his favorite parts from the famous Sanskrit poetry Satkatriya was vanquish enemies at arms, gain mastery of the science and varied arts. You may do all this, but karma's force alone prevents what is not destined and compels what is to be. In late 1938, scientists found that the nuclei of uranium atoms could be split when hit by neutrons. During this process, a small amount of mass is lost from the split uranium nucleus, but this loss corresponds to an immense amount of energy, as described by Albert Einstein's famous equation E equals to mc square. Shortly after the discovery of nuclear fission, it was confirmed that each fission reaction produced the release of 2 or 3 neutrons. These secondary neutrons can go on to fission other nuclei and continue to do so until all uranium is fissioned. This crucial characteristic allows for the possibility of a chain reaction. On January 29, 1939, physicist Luis Alvarez was getting a haircut when he came across a news story reporting that Otto Hahn and Fritz Strassmann had successfully demonstrated nuclear fission. Alvarez was astonished and rushed to inform Oppenheimer, who initially found it impossible. But the next day, Alvarez successfully repeated the experiment in his lab. Oppenheimer was awestruck and immediately agreed that the reaction was authentic. He also speculated that in the process, extra neutrons released as a result of fission could be used to split more uranium atoms and thereby generate power or make bombs. He was right, at least in theory. But the process of making a bomb wasn't that simple. The first hurdle was political. Leo Szilard, a Hungarian-German-American physicist who was well aware of the realistic potential for an atomic bomb, was horrified at the idea of Hitler getting this technology first. Szilard persuaded Albert Einstein to sign his name in a letter addressed to President Franklin Roosevelt. The letter warned the president of the dangers of the bomb and suggested that Germans might already be working on such a weapon. Einstein's letter led President Roosevelt to establish an informal uranium committee, which was tasked with coordinating research and development efforts for creating an atomic bomb. Though for 2 years, nothing happened. The MAUD committee, which was the British Scientific Working Group, produced a classified report titled The Use of Uranium for a Bomb. The report indicated that a bomb utilizing plutonium or uranium could be compact enough for existing aircraft and potentially constructed within 2 years. This led the White House to now begin to organize the government's enormous resources to recruit scientists from around the world to work on a bomb project, otherwise known as the famous Manhattan Project. The project would go on to employ as many as 125,000 personnel by mid-1944 and reach an expenditure of around $2 billion by the August of 1945. Leading such a massive effort, that too in extreme secrecy, required an extraordinary leader who had the authority to lead a group of some of the brightest minds of the time. In 1941, Ernest Lawrence wrote to Arthur Compton that Oppenheimer was the only guy he knew of who can make the atomic bomb before Hitler does. General Leslie Groves, who was tasked with leading the Manhattan Project, met Oppenheimer at Berkeley. Initially, Groves hesitated to appoint Oppenheimer due to his lack of Nobel Prize, administrative experience, and certain political background aspects. However, Oppenheimer's compelling insights convinced Groves to hire him.
First meeting with Groves was at the house of the president of the University of California. I said, this thing will never get on the rails unless there is a place where people can talk to each other and work together on the problems of the bomb. And this could be at Oak Ridge, it could be some California desert, but someplace there's got to be a place where people are free to discuss what they know and what they don't know and to find out what they can. And that made an impression on him.
The next task on the list was to find a location. Oppenheimer proposed Los Alamos as the ideal site. Oppenheimer found himself back in New Mexico, but this time to bring physics there. Physics and New Mexico were now combined.
Suddenly we knew that the war had arrived here, and these two characters showed up, Mr. Smith and Mr. Jones, one wearing a pork pie hat and the other a suit and a normal hat. And these two guys went around as if, well, one, they owned the place, which evidently they did, but more than that, as if their pseudonyms was a normal sort of thing to do. My God, I mean, there their pictures were in our physics book, and we all had physics. One is the lead theoretical physicist of his age, and the other head of a major laboratory who had done the cyclotron and things like that. So we immediately knew that, one, they felt that it was so important to be Oppenheimer and Lawrence that they had to have a pseudonym. Two, that they were putting megabucks, multi-megabucks, into what seemed to us the worst place in the world to have a laboratory.
Within days, the Army began the process of acquiring the site, which later became known as Site Y. Oppenheimer's recruitment efforts for the Manhattan Project began in the autumn of 1942, targeting top scientists like Hans Bethe, Robert Bacher, Edward Teller, Robert Christie, Robert Wilson, and many others. Among them was a young physicist, Richard Feynman. Recognizing Feynman's brilliance, Oppenheimer was eager to have him join the team at Los Alamos. However, Feynman's wife, Arlene, was suffering from tuberculosis, and Feynman was unwilling to relocate without her. To resolve this, Oppenheimer founded a tuberculosis sanatorium in Albuquerque for Arlene and assured Feynman that he could work at Los Alamos while visiting his wife on weekends. And now, Feynman was in the team. Without delay, he initiated a covert summer seminar gathering a select group of esteemed theoretical physicists. His priority invitees included Hans Bethe, Edward Teller, Felix Bloch, Robert Serber, and former students such as Robert Wilson. Oppenheimer fondly referred to them as his luminaries. Every physicist knew that German scientists had a 2-year lead, particularly after Oppenheimer learned that Heisenberg had been appointed director of a nuclear research facility in Berlin not too long ago. They all knew what was in the line, and after 4 years of the discovery of fission, Los Alamos opened in March 1943. The community had numerous buildings, including a plutonium purification plant, laboratories, and offices. Oppenheimer in Los Alamos was different from what people had known him for. He transformed from a prodigy to a charismatic intellectual leader. Oppenheimer's intellect, intuition, and interpersonal finesse led to an extraordinary collaboration surpassing all expectations. He was a remarkable host, swiftly summarizing papers and staying informed about all lab activities. Finally, Oppenheimer had to structure Los Alamos.
Two advisors to Oppenheimer, namely Bacher and Rabi, who was associate director of the radiation lab, were advising Oppenheimer and told him, well, it's impossible to run the lab with 20 independent groups all funneling into your brain. You have a marvelous brain, but you can't direct all of this yourself. You have to have a structure as the radiation lab had, namely the lab was first divided into divisions, each division having maybe 5 to 10 groups, and each group having maybe 5 to 10 scientists in it.
He organized the lab into 4 key divisions, including experimental physics, theoretical physics, chemistry and metallurgy, and ordnance.
And they then recommended to Oppenheimer to appoint me as the leader of the theoretical division.
The lab operated around the clock, with flexible schedules and no time clocks. The team worked tirelessly, constantly refining their technique through trial and error, and Oppenheimer led the team of scientists in designing a fission device small enough for military deployment. To create it, they needed to utilize fissile material capable of undergoing fission with neutrons. Uranium is the element capable of sustaining a nuclear chain reaction. However, there was a challenge. Natural uranium consists of only 0.7% uranium-235 isotope and 99.3% uranium-238 isotope. The uranium-238 isotope, although abundantly available, requires high-energy neutrons to undergo nuclear fission, which is not desirable. On the other hand, uranium-235 is a fissile material and readily undergoes a chain reaction. The only problem is, it is not readily available. And therefore, the initial and crucial challenge was the production of uranium-235 isotope. One of the methods deployed during World War II was electromagnetic isotope separation, or EMIS, and was facilitated by Ernest Lawrence's new device, the calutron. The calutron was a hybrid of the cyclotron and a mass spectrometer. The extraction process is based on a simple mass spectrometer principle, which states that a charged particle will follow a circular path when passing through a uniform magnetic field. The key distinction between uranium-235 and uranium-238 lies in their slight difference in weight, with uranium-235 being slightly lighter due to its 3 fewer neutrons. As a result, the heavier uranium-238 ions will travel a large radius compared to the lighter uranium-235 ions, enabling the separation and collection of the isotopes in receivers. Once the uranium-235 was produced, the next challenge was to design a bomb. The uranium bomb, or famously known as the Little Boy, was assembled using a gun-type design. It involved a barrel with uranium masses at 2 ends, each slightly below the critical mass required for nuclear fission. Individually, they lack enough mass to initiate a nuclear reaction. When the explosion occurs, it propels one piece of uranium mass towards the other. As the first mass collides with the second one, a nuclear chain reaction is triggered, resulting in the release of immense energy. This bomb had the potential to create a massive explosion equivalent to 20,000 tons of TNT. They simultaneously worked on the plutonium bomb. Unlike uranium-235, plutonium was easier to produce by bombarding uranium-238 isotopes with neutrons.
In the middle of the Los Alamos experience, it was discovered by Segre that plutonium, in fact, the isotope plutonium-240, had an exceedingly high spontaneous rate of fission. It fissions at a rate which was so fast that our chosen method of assembling a bomb, namely by shooting one piece of material into another target, would not work. On the way of, on the flight from the gun to the target, the fissile material would already become critical and begin reacting, and we would get a very low yield, a fissile. So another method of assembly had been suggested by Neddermeyer, namely to take the shell of fissile material and surround it by explosive. In that case, you could get speeds about 10 times higher than you could get from a gun, and you would have an implosion.
Oppenheimer explored an implosion design, which was supported by John von Neumann's calculations, demonstrating its theoretical feasibility. The implosion design's concept involved triggering explosions all around the core of the plutonium bomb, famously known as the Fat Man, while ensuring precise and symmetrical implosion of the core. This innovative approach resulted in a significantly reduced core size, increasing its density and facilitating a nuclear chain reaction. To enhance the implosion process, they incorporated a neutron-producing device at the center of the bomb called Urchin. The Urchin consisted of a layered structure with beryllium and polonium separated by gold and nickel. The implosion caused the Urchin to undergo its own reaction, producing neutrons that further facilitated the chain reaction in the core. Concerns were raised about the possibility of an atomic bomb causing a catastrophic explosion in the Earth's atmosphere. When Oppenheimer shared this information with Compton expressed his belief that it might be preferable to accept the Nazis' tyranny rather than risk an event that could lead to the ultimate downfall of humanity. The bomb was nearing its completion. Suddenly, the circumstances of World War II changed. Before the completion of the bomb, on April 30, 1945, Adolf Hitler committed suicide, 8 days after which Germany surrendered. With Japan continuing to resist surrender, the United States government and the military leadership made the decision to deploy the atomic bomb against Japanese cities as a means to compel Japan to surrender and bring an end to the war in the Pacific. The realization that the atomic bomb would not be used against the Germans but against the Japanese raised doubts and questions in scientists working in the Manhattan Project. Oppenheimer argued that the world should be informed about this new weapon. Keeping it a military secret would only pave the way for future wars fought with atomic weapons. Despite these doubts and questions, the efforts to complete the bomb were in full swing. The famous Potsdam conference was scheduled to take place on July 17. It was essential to test the bomb's capabilities before the conference to provide the United States with valuable information regarding potential use of atomic weapons and discussing strategies for dealing with Japan and ongoing war in the Pacific. After Groove's continued pressure, Oppenheimer set a target date of Monday, July 16. Oppenheimer named the site Trinity, perhaps drawing inspiration once again from the Bhagavad Gita and its trinity of Brahma, Vishnu and Shiva, symbolizing creation, preservation and destruction. On the evening of July 11, he bid farewell to his wife Kitty and told her that if the test was successful, he would get a message to her saying, "You can change the sheets." 2 days prior to the scheduled test, Oppenheimer, Vannevar Bush and other officials from the S1 committee arrived in Albuquerque. On the morning of Sunday, there were unpredictable winds and incoming storm. Tensions heightened as test firing indicated potential failure. In an attempt to alleviate the mounting tension, Oppenheimer recited a translated stance from the Bhagavad Gita: "In battle, in forest, at the precipice in the mountains, on the dark great sea, in the midst of javelins and arrows, in sleep, in confusion, in the depths of shame, the good deeds a man has done before, defend him." But as the time of the test approached, the skies cleared and the wind calmed. Sam Allison, the Chicago physicist voice, signaled the approaching moment, saying, "It is now 0-20 minutes. Alexander Kistiakowski, the head of the explosives division, offered a friendly wager, betting his own month's salary against Oppenheimer's humble $10, assuring him that the implosion charge would indeed prove successful. Tension filled the air as seconds ticked off. He said, "These things are hard on the heart."
Told us there was 20 seconds or something to go. The people that were far away like we were, the others were closer, 6 miles away. And they gave out dark glasses that you could watch us. Dark glasses. We're 20 miles away from the damn thing. We think it's dark glasses. I said, they're going to see a damn thing through dark glasses. And so what I figured, the only thing that will really hurt your eye, bright light never can hurt your eye. It's ultraviolet light that does. So I got behind a truck windshield so that the ultraviolet can't go through glass, so that would be safe. And so I could see the damn thing. Other people were never going to see the damn thing.
Lying face down outside the control bunker, Robert Oppenheimer awaited the final countdown. With a burst of light and the following deafening roar, the explosion finally came.
And this tremendous flash out there, so bright, my head goes like this because it was so bright. And I see this purple splotch on the floor of the truck. And so I turn back up and I see this white light changing into yellow and into orange. The clouds form. and then they disappear again. The compression and the expansion forms and makes clouds disappear. And then finally, a big ball of orange. It became a center that was so bright, became a ball of orange. It started to rise and billow a little bit and get a little bit black around the edges. And then you see it's a big ball of smoke.
The test worked beyond all expectations. I had calculated, or rather Serber had calculated, it would give 8 kilotons of energy. But one of Serber's young men had calculated it might give 20. And of course I believed authority, I believed Serber. So I said it would give 8 kilotons, and it gave 20. So it was successful beyond all belief, and thereby established the plutonium nuclear weapon. It was then a duplicate of that was then dropped on Nagasaki a little later.
The profound impact of the explosion left the men in a state of unfiltered euphoria. In the aftermath of the explosion, the men embraced each other, laughing and shaking hands. Oppenheimer's face relaxed into immense relief. A weight lifted. While we can only wonder what thoughts raced through his mind, his brother remembered their shared words. It worked. Later, when approached for comment by a reporter from the New York Times, Oppenheimer described the blast as terrifying but not depressing. He added, "Lots of boys, not grown up yet, will owe their life to it." Kisiakovsky playfully reminded Oppenheimer of their bet, though Oppenheimer's wallet was empty. Later in Los Alamos, Oppenheimer ceremoniously presented Kisiakovsky with an autographed $10 bill. On August 6, 1945, Little Boy was dropped on Hiroshima, and then 3 days later, on August 10, 1945, Fat Man was dropped on Nagasaki.
A short time ago, an American airplane dropped one bomb on Hiroshima and destroyed its usefulness to the enemy. That bomb has more power than 20,000 tons of TNT. With this bomb, we have now added a new and revolutionary increase in destruction to supplement the growing power of our armed forces. In their present form, these bombs are now in production, and even more powerful forms are in development. It is an atomic bomb. It is a harnessing of the basic power of the universe. The force from which the sun draws his power has been loosed against those who brought war to the Far East.
I have been asked whether, in the years to come, it will be possible to kill 40 million American people in the 20 largest American towns by the use of atomic bombs in a single night. I am afraid that the answer to that question is yes. I have been asked whether there are specific countermeasures against the atomic bomb. I know that the bombs that we make in Los Alamos cannot be exploded by such countermeasures. I do not think there is any foundation for the hope that such countermeasures will be found. I have been asked whether there is hope for the nation's security in keeping secret some of the knowledge which has gone into the making of the bombs. I am afraid there is no such hope. I think the only hope for our future safety must lie in a collaboration based on confidence and good faith with the other peoples of the world.